This is the answers portion of the video, lesson 2 of the course Real Analysis. Question 1, part A. The arity of this relation is clearly 3 as it is defined on 3 points. Part B. The arity of this relation is 2. For further research, note that if B is related to A, then B divided by A is a golden ratio. Part C. In traditional geometry, there is no fixed number n for which n points constitute a line. There are other geometries which give different definitions for a line, but usually a line is thought to be comprised of an infinite number of points. You could extend the definition of a relation to include infinite arities, but in this case we will simply say that the relation is not a finitary relation, and as far as we are concerned is not a relation. Question 2. These relations are most sensibly defined on the following domains and codomains. Part A. We need only exclude 0 from both the domain and codomain, as if x or y is equal to 0, then the predicate cannot be evaluated. In all other cases, we can evaluate it. Part B. For the membership relation, we have an element of x on the left-hand side and the set x on the right-hand side. So the relation is defined on the Cartesian product of x and the set containing x. Part C. The universal set in this case is the integers, so the predicate can only be evaluated on the elements of the set comprised of 0 and 2. Question 3. Part A. The image is a set of all integers greater than 107. Part B. To find the image, we take the union of the images of the elements, and to do so we solve the equations where 4 equals y squared, 16 equals y squared, and 25 equals y squared, which is this set. Part C. The pre-image is a set of all prime numbers, because no integer greater than 1 divides a prime number. Question 4. The resultant relations are the following. Part A. The set comprised of the ordered pairs 5, 0, 3, 0, 1, 9, and 2, 9. Part B. The greater than or equal to relation. Part C. The equality relation. Part D. The strictly greater than relation. Question 5. Part A. There are 9 possible relations, and these 9 can either hold or not, meaning there are 2 to the power of 9 possible relations, including the null and trivial relation. Part B. In this case, there are 10 relations that can vary, as 6 are identical, meaning there are 2 to the power of 10 relations. Part C. There are 6 relations that are fixed, and 15 that can vary, as the other 15 are identical, meaning there are 2 to the power of 15 relations. Part D. The Cartesian square of the empty set is the empty set. There is only one subset of the empty set, meaning there is only one possible relation on the empty set. Question 6. This is virtually identical to the proof for Theorem 1. Rather than having it read out, pause the video and make sure your proof is consistent with this one. Question 7. Your diagram may have looked like this. If you start from any number and head downwards, you will always find the divisors of that number. You may have noticed that this is an example of a Hasse diagram. Question 8. In this proof, we need to show that if AB belongs to the composition, then BA belongs to the composition too. For step 1, we see that by the definition of a composition, that there must exist an element C belonging to set A, such that AC belongs to inverse R, and CB belongs to R. Then, using the definition of an inverse relation, we see that BC must belong to inverse R, and CA must belong to R. Now, we work the definition of a composite relation backwards to see that BA belongs to the composite relation too. This completes the proof. Question 9. Given R as a subset of A cross B, and S as a subset of B cross C, we need to show that the image of R composed of S is never the empty set for any set X belonging to the domain of R. We use the alternative notation for a composition to prove this. As the image of X is never the empty set by R being left total, we will say that the image of X is some non-empty set A, where A is either B or a proper subset of B. Then, the image of A under S is not the empty set either, by S being left total. So the image of X under the composite relation is never the empty set for all X. This completes the proof.